Let's say you went out for a run or something and you got your heart rate up and you want to know what your heart rate was. You're going to need to do two things. One, you're going to have to count beats. Two, you're going to have to keep an eye on the time, which was always the hard thing for me, to not count with the time. But if we take that idea and carry that into chemistry and talk about rates of reaction, what do we do with that? Well, let's remind ourselves what a rate is, and then we'll be more formal with it, and then we'll talk about then chemical reactions. It's how fast or slow something is happening. So something has to be happening, and it has to be happening in a short period of time or in a long period of time. So like we were talking about a moment ago, beats per minute, if you're talking about your heart rate, or if you're talking about a rate of speed in a vehicle or something, it's kilometers per hour or something. But there's some kind of measurement with time. Well, if I'm talking about reactions, what am I going to be measuring? I'm going to be measuring either how fast a product is being produced, or, if it's more convenient, how fast a reactant is getting used up or consumed. So then, if I want to formalize that, the reaction rate is how fast the concentration of reactants is changing over time, or how fast the concentration of products is changing over time. And we don't very often use those square brackets to refer to concentration, but in this case we will. Concentration is typically going to be moles per liter. So when we're talking about rates, it's moles per liter per second, or perhaps moles per liter per minute, depending on the speed of the overall reaction. It's also important to realize that the rate of a reaction is not constant. During the beginning of a reaction, where you've got lots and lots and lots of reactants, the rate is going to be fairly quick. But as the reactants get used up and it's harder for them to find each other to react, the rate is going to slow down. But there will be times during the reaction where it's fairly steady from a starting point to a finishing point. Well, I used reactants and I used products before. How do I know which one to use? And the good news is it really doesn't matter, because they're going to be related within the chemical reaction. So let's say I was looking at this reaction and I wanted to chart, or I wanted to measure its rate. If I somehow were able to determine that the rate of consumption of methane, CH4, was 0.2 moles per liter per second, well, that means that also the consumption of chlorine would be the same, because 1 mole reacts with 1 mole. And likewise, the rate of production of products, because 1 mole reacts with 1 mole to produce 1 mole and 1 mole, the rate of production of both products would also be the same. Well, what if the numbers were different? Glad you asked. So they would still be related. That's the key part. So in this reaction, 1 mole reacts with 3 moles to produce 2 moles. So if I were to measure the rate of production of ammonia, NH3, to be 0.005 moles per liter per second, then if I wanted to look at the consumption of nitrogen, I could use this formula. And I want you to pay attention to the second piece, or the last piece there, the 1 mole of nitrogen for every 2 moles of ammonia. And if that looks like stoichiometry, A, relax, relax. But B, yeah, because it's the same kind of idea, that those two things are related based on their balancing coefficients. So the rate of production of ammonia divided, times 1 divided by 2 is going to be the rate of consumption of nitrogen. Okay, what about the rate of consumption of hydrogen? Well, it's going to be consumed at a rate of 3 to 2 if we're comparing with the ammonia. So the balancing coefficients become part of my ratio, and I can use that to determine the rate of consumption of hydrogen. Now, I also want to point out that algebraically, products are going to be increasing, and so you'll have a plus sign, and reactants are going to be decreasing, so they could come out as a negative sign, but it doesn't really affect what we talk about when we say the rate of reaction. But we do have to say the rate of reaction is 0.002 moles per liter of this, so that we know. Okay, here's how all of those three things would be related within that reaction. Do we really need that? No. So if you're iffy on that one, but if I were to measure one thing and compare it with the others, they would be related based on their balancing coefficients. And then if the reaction got larger or more involved, same kind of thing would apply. Okay, in terms of introduction to rates, without having a lot of actual numbers, this is it. This is what we've done. We are going to have to, though, learn how to, once I know what the concentration is, turn that into a rate. So we're going to be doing some graphing, charting, if you will. We're going to be doing some measurement. We also have to figure out, well, if all of those concentrations are somehow related, which one would I pick? And that kind of depends on what's easy to measure. But we'll talk about that a little bit later in class.